of J differ by any other number, then integral actually goes to 0, and that's the reason why you don't have any intensity in those transitions. This was a selection rule for an absorption process. In a Raman process, and today we will try to rationalize this not by looking at those integrals. Again, the same thing. How do I take this? Take my psi prime, take my psi double prime, put the wave functions, put a polarizability in between, evaluate the integral, and see what you get, and you will get it. But instead of doing that, let's see if we can rationalize this in some other way, which is more appealing. I didn't do it earlier because I was going to wait for Raman spectroscopy to be handled before we did this. Let's see what happens in Raman spectroscopy. I have a molecule in a state J double prime. It absorbs, I should say, interacts with a photon. And what's the angular momentum of a photon? 1 unit of angular momentum in terms of H cross. So I just say 1. And what do I get eventually? I get another molecule. I get the molecule. Let's say some other state, J prime. I'm looking at rotation levels now. Plus the scattered photon. And what's the angular momentum of the scattered photon? For a photon, the angular momentum is 1. So therefore, and the angular momentum has to be conserved in this process before and after. So if this has to be conserved, this is plus, of course it could be plus or minus 1. But if this was plus 1 and this was plus 1, then what should be J prime and J double prime? They have to be the same. There is a J equals 0. If this was plus 1 and this was minus 1, what should happen to this fellow? That's sitting out here. Okay, these are three possibilities. The photon can be with 1 unit of angular momentum in both cases. Could be plus 1 and minus 1 in this case, or a minus 1 and a plus 1 in this case. And therefore, if you put in all these three possibilities, you will find that this J and this J must be related by either 0 or plus minus 2. And so you can actually look at the selection rules as implying the conservation of angular momentum in this process. If I do a simple absorption experiment, which is what you did earlier, how does the picture change? The picture changes because now it is M molecule in J prime plus 5 with some angular momentum 1 or minus 1, giving me M. There is no photon out here. So what should the relationship between this and this be? It can only be plus 1 or minus 1. And that's the reason why you find that, in fact, it actually goes the other way around. People have actually rationalized the angular momentum for the photon with all these experiments. The fact that you have a 0 plus minus 2 for a Raman experiment and a plus minus 1 for a pure absorption experiment in rotation spectroscopy actually tells me the only way you can explain all this is if this fellow out here has an angular momentum of 1. And that's how you can actually rationalize why the selection rule of 0 and plus minus 2 would have to occur. What was the plus minus 1 branch called? If delta J was plus 1, R branch. And minus 1 was S branch. Now I have plus 2. Oh, P and R branches. We are getting to S branch now. Right? And then what happens? We have plus 2 possibility, we have a minus 2 possibility, and we have a 0 possibility. So now you have O, P, Q, which is my delta J equals 0, which you would not see in an absorption experiment. You have R and you have S. And that's basically the branch structure that we would see in a Raman spectrum. In a Raman spectrum, you want to see O, you might see Q, you will see Q, and you will see the S branch. So you see O, Q, and an S branch in the Raman rotation spectrum. And what will you see in an absorption spectrum? You will simply see the P and R. At the end of the day, the sort of information that you're going to get with both techniques will be identical. But it's not so identical because if you try doing this experiment of rotational spectroscopy with nitrogen, You don't get an absorption spectrum. You don't see the P and R branches ever. But you can get the O, Q and the S branch, and from which you can get information on the bond length for hydrogen, bond length for oxygen, bond length for C2, none of which are rotationally active in an absorption experiment, but all of them are Raman active in a rotation experiment. So what we will do is, now that we know the selection rules are 0 plus minus 2 and we have some physical intuition as to why it should be the case, in the next class what we will do is to go on and build up this the ladder of spectral lines similar to what we saw earlier and reconstruct what one would see in the rotational Raman activity.